Training a deep neural network from scratch often creates a highly unstable learning curve. The erratic loss surface makes finding an optimal solution difficult. To tame this volatility, batch normalization has become the standard mechanism for stabilizing internal layer dynamics. This chart shows the loss values of our models over 20 epochs. When we compare a standard LeNet model to one using batch normalization, the gap in these curves reveals a significant leap in training efficiency. By the end of this session, you will build a custom convolutional neural network and prove this performance gap yourself on a challenging dataset. Step 1 is establishing a reproducible environment. We set fixed random seeds across all libraries, so our experimental results can be reliably verified. Next, we define a structured configuration block for our dataset and training variables. This keeps our hyperparameters organized in a single Python data class. For this run, we cap the training at 20 epochs and set our learning rate to 1e⁻². Locking these configurations in place gives us the baseline control we need to measure the specific impact of our architectural changes later in the experiment. We are using the Fashion MNIST dataset. It offers a more complex visual challenge than standard numerical digits, pushing our network to learn intricate patterns. The model has to classify 10 distinct clothing categories, ranging from coats to sneakers and sandals. Before we pass this data to the network, we have a dimension problem. The standard LeNet architecture expects 32 by 32 pixel inputs, so we must explicitly resize our native 28 by 28 images to fit. We handle this inside a pre-processing pipeline. The image pre-processing transforms function resizes the images and converts them directly into PyTorch tensors. The final pre-processing step is data normalization. For Fashion MNIST, we must apply its specific pre-computed mean of 0.2860 and a standard deviation of 0.3530. If we skip this precise formatting, the model processes skewed data. Even with architectural improvements, the network cannot learn effectively if the inputs are not properly standardized. Now we build the LeNet 5 architecture. We structure this model into two parts, the convolutional body, which extracts features, and the fully connected head, which outputs the final classes. The initial input data flows straight into the feature extractor's first standard convolutional layer. This is the precise location to inject our batch normalization logic, after the convolution but before the ReLU activation function. By placing it here, we normalize the raw outputs. This forces the data into a stable, centered distribution before it hits the nonlinear activation threshold. This precise architectural sandwich prevents internal covariant shift during deep training, ensuring that the distribution of inputs to subsequent layers remains consistent. With our architecture defined, we run two simultaneous training pipelines, one baseline LeNet 5 model and our updated model with batch normalization enabled. This chart plots the validation accuracy of both models. The dashed line represents the batch norm model, which achieves a high accuracy threshold much earlier in the run. This chart illustrates the training and validation loss over 20 epochs. At epoch 2, the batch norm model dramatically outpaces the baseline, its dashed line dropping sharply to show a clear acceleration in convergence. These empirical graphs prove that batch normalization doesn't just stabilize the learning curve, it significantly reduces the time required for the model to find an optimal solution. We now evaluate the model on unseen test data. It correctly categorizes structurally unique items like sneakers and sandals. However, edge cases remain. Here, the model confuses a coat for a shirt due to similar pixel silhouettes. While an optimized architecture accelerates learning, the absolute accuracy ceiling is ultimately dictated by the inherent visual ambiguity present within the dataset itself. We built the baseline, injected the normalization logic, and used empirical evidence to prove its efficacy over 20 epochs. Normalizing intermediate outputs before activation is the mechanism that maintains a consistent data distribution, preventing the erratic shifts that stall deep network training. Now that you've mastered this setup on LeNet 5, your next challenge is to apply these exact normalization concepts to a much deeper architecture, like ResNet. Mastering this foundational technique is the essential gateway to stabilizing and scaling any advanced deep learning project.